Okay, so for this course of general topology, the basic requirement is real analysis and metric spaces. And before starting, let me show you the syllabus. Is this visible to everyone?
Yes, sir.
Yes, sir.
Okay. Actually, this syllabus is already available on your departmental page, departmental website. So you can download from there. And so according to your syllabus, look, the name of the subject is general topology. Its course number is MMM1009. So here requirement is real analysis and metric spaces. So revise it. Real analysis. Even last year lectures of real analysis is already available on YouTube. So you can go to playlist and from there you can revise it. And metric spaces. And you can see that unit 1 is basic concept and point set topology. So in this we will start from this topology and topological spaces. But before coming to this, let me name you the book mentioned in your syllabus. We have to cover from this one is the key book, I mean reference book. Actually this syllabus is designed from this book, and we will cover most of the results from this book, and for examples we will follow this one. So all these 4 books are very important. This topology by Munkres, James R. Munkres. So, and second one, this one also contains very good examples. Essential Topology by Martin D. Crossley. I will discuss some examples also from this book, and then a lot of problems from competition point of view. I mean, if you want to prepare for NET, GATE, and JRF, then this book is very good. But for theory purpose, there is no substitute for this book. These two, for theory purpose, these two are very important. 1 and 3. Basic Topology by M.A. Armstrong. Now just go through these topics mentioned in your unit 1 of the syllabus. We are going to first cover the basic concept of point set topology. So in this we will see various examples, what we mean by topology and what are different topological spaces, examples of topology including discrete topology, indiscrete topology, standard topology on our lower limit and upper limit topology, co-finite topology, and co-countable topology, topology induced by a metric, basis for a topology, subspace topology, K topology. So, and then we will come to order topology. This one is also in your GATE syllabus, product topology. So this syllabus is designed keeping in view your requirement for NET and GATE also. Topology generated by sub-basis, closed sets and limit points in topology. Neighborhoods, interior, exterior, boundary points, derived set, Hausdorff spaces. We will see whatever we have studied till now in real analysis and metric spaces. We will find various exceptional cases in topology. We will see various those. There are several results which you will see that they are holding in metric spaces, but they may not prove in topological spaces. So we need to take care of all those results. Unit second. This is continuity, and after continuity of functions, we will study homeomorphism. This one is an important property. Homeomorphism, yes. After continuity, we will study homeomorphism and those properties which are preserved under homeomorphic map. Out of them, connectedness and proper compactness are 2 topological properties which are preserved under. There are more than connectedness, compactness, more topological properties which gets preserved under homeomorphism. Any property which gets preserved under homeomorphism is called topological properties, and out of that we will study these 2 cases, so connectedness and compactness. This one is also very important from competition point of view. Everywhere you will find in interview and I mean all those exams like NET, GATE, JRF, you'll see various questions from this section. And then I will come to countability and separation axiom, in which we will study this normal regular Hausdorff spaces, T's extension theorem, Eurytion's lemma, T's extension theorem. Basically, we will see that there corresponding to some topology, you will see that there exists a metric which may generate that topology. So those topological spaces are called metrizable, which are generated by metric. But in general, this is not true. So guarantee of metrizable space. I mean, if a topological space is metrizable, then how to show that a topological space is metrizable? We need to take help of this Eurytion's lemma, Eurytion's theorem. And similarly, there is a T's extension theorem. And then I will come to product spaces and quotient spaces. So we will see this, say, there are various exceptions you will study in box topology, product topology. Like, in case of function of several variables, if you recall that in advanced calculus, you have studied in function of several variables that if f is a map from say R2 to R2 and given by f of xy equal to say sin x comma cos x. So if the slot functions are continuous, then f will be continuous, and if f is continuous, all slot functions will be continuous. I've been talking about function of several variables. So basically this result is true in case of this product topology. But when you move to this box topology and uniform topology, you will see various exceptions. Those results may not be true. Then again, we will come to quotient topology. Quotient topology, this one is very interesting topic, quotient topology, how to identify spaces. So we will look various examples from this one. So before starting, I would like to recall some of the basics from this real analysis and metric spaces. So this is your reference book, Topology by G.R. Munkres, second edition. And from this, because see, we are starting late, so I will be little bit fast after unit 1, not in unit 1. So here the things I need to cover is from this chapter 2, topological spaces and continuous function. Okay. Yes, tell me the difference between finite and infinite set. Yes, anyone? Yes, how one will define finite and difference between finite and infinite set? तो आप लोगों ने पढ़ रखा है ना ग्रेजुएशन में सब, मेट्रिक स्पेस या रियल एनालिसिस शुरू करने से पहले अक्सर फाइनाइट इनफाइनाइट सेट, काउंटेबल अनकाउंटेबल सेट डिस्कस करते हैं. कोई बोलना चाहेगा? नहीं, क्लास थोड़ी इंटरेक्टिव हो तो हमें मालूम चले कहाँ से पढ़ाना है.
Sir, a set is said to be finite if it is empty, or it is equivalent to a set say 1 2 3 up to n. अगर एक set बना ले 1 2 3 up to n where n belongs to natural number. अगर if a set is equivalent to this set.
Yes, फैजान. हाँ, ठीक है फैजान, सही कह रहे हैं आप, बिल्कुल सही है.
And infinite set, if it is not finite, it means it is non-empty and it is not equivalent to this set which I formed.
The set Gn 1 to n.
Yes, sir.
Yes, basically this one is the standard definition from book of Rudin, Walter Rudin. Okay. And can you tell me one of the any property which differentiate between finite and infinite set? Okay, your definition is okay. So as per your definition, see, empty sets are always assumed to be finite.
Yes, sir.
So, and a non-trivial set is said to be finite if it is similar, I mean bijective to the set 1 to n. This
1
set.
to n. Yes, sir.
Just let me share, because these are the some basic things which I am going to revise. I will use in between. So just go through my lectures on those are all available on YouTube, in which I have already discussed all these things. Here just I am recalling. So any set subset of R is said to be finite if S is similar to this set Gn, where Gn is equal to 1, 2, 3, sorry, 1, 2, 3 up to n. Okay. So if any set is similar, whenever I say similar means there exists at least one bijective map. There exists at least one bijective map. Two sets are said to be similar. Two sets are said to be similar if there exists at least one bijective map between A and B. So two sets A and B, this is the notation used for similar bijective if there exists at least one bijective map between A and B. Okay. So any set is said to be finite if it is similar to this Gn subset of n, 1 to n. So see, empty set is assumed to be finite. Okay. I have taken this definition from book of W. Walter Ruding. And infinite set, yes, infinite set, either it will be countable or uncountable. See, finite sets are already countable, but a countable set can be infinite, can be finite. Okay. So now what, yes, how one will define countable? देखिए मुझे क्या पढ़ाना है, शुरू के 2-4 लेक्चर
Set is said to be countable if it is finite, or countably infinite, that is denumerable.
हाँ, denumerable या countable एक ही है, countably infinite. Yes, it is said to be countable if it is similar to set of natural number.
Natural number.
Yes. Remember that S should not be equal to 5. S should not be similar to Gn. पहले तो ये होना चाहिए, नॉन एम्प्टी होना चाहिए, और ये Gn के सिमिलर नहीं होना चाहिए, और साथ में किसके सिमिलर होना चाहिए? सेट ऑफ नेचुरल नंबर. Similar to set of natural number means there exists at least one bijective map. Okay. So, yes. And what about uncountable?
Which is not countable.
Which is non-empty, not similar to Gn, and not similar to set of natural number. Key points समझ में आया? A set is said to be uncountable if it is if it is non-empty, if it is not similar to Gn, if it is not similar to set of natural number.
Sir, can we say fields to onto?
Yes.
Okay, sir.
हाँ बताएं क्या कह रहे हैं?
सर हम कह सकते हैं क्या ये फेल्स करेगा onto नहीं होगा uncountable set?
नहीं, देखो जैसे वो तो कंपैरिजन के लिए यूज करते हैं. बेसिकली इफ यू नो दैट सेट A is infinite, say uncountable. If you know that set A is uncountable, and just show that cardinality of set B is greater than equal to cardinality of set A, then this implies that B is also uncountable.
Yes, sir.
Okay. And if suppose some set C is countable, and just show that cardinality of A is less than equal to cardinality of C, this implies A is countable. A is countable. So for those cases we will use here 1 1, and here we will use onto. Okay. So I will, you can go through my those lectures which already I have recorded and posted on YouTube. In those lectures I have discussed in detail. Here I am not going, just I am recalling that what we mean by countable and uncountable set. Yes, any property which differentiate between this finite and infinite set. बताएं कोई ऐसी प्रॉपर्टी।
Z is countably infinite set.
ठीक है, वो एग्जांपल ठीक है, जैसे यहाँ पे काउंटेबल z एग्जांपल z ले लिया।
Cardinality of finite set is 0 or n, but infinite set it doesn't mean has मतलब it has no existence of cardinality.
नहीं, वहां पे तो इनफाइनाइट सेट में बेसिकली कॉन्सेप्ट ट्रांसफाइनाइट नंबर का यूज करते हैं। कार्डिनलिटी वगैरह फाइनाइट सेट के लिए ये जो नोटेशन यूज करते हैं ना, फाइनाइट सेट के लिए यूज करते हैं।
Yeah, okay sir.
z हुआ, सेट ऑफ नेचुरल नंबर हुआ, ये सारे क्या है? काउंटेबल। सेट ऑफ इंटीजर्स, सेट ऑफ नेचुरल नंबर, होल नंबर। अनकाउंटेबल सेट में जैसे रियल नंबर हो गया, इंटरवल्स हो गए, नॉन ट्रिवियल इंटरवल्स।
Okay sir.
वेरी इज नॉट इक्वल टू बी, कोई भी इंटरवल, ये क्या हो गया? अनकाउंटेबल सेट के एग्जांपल हो गए। ठीक है, देखो, a finite set will never be similar to its proper subset. Can I say that a finite set is never similar, never similar to any proper subset? Similar means there exists at least one bijective map. चलो, अगर आपको नहीं समझ में आया तो एक काम करो, मैं यहां समझा देता हूं, इस चीज को यहां समझाता हूं। ठीक है, just for understanding purpose, let us take set A is equal to this 1 2 3 4. Take its any proper subset. Let me take B is equal to 1 2 3. Sorry, B is equal to 1 2 3, just for understanding purpose. Then can you tell me a bijective map between this 1 2 3 and this element, say 1 2 3 4? Bijective means 1 1 and on 2. So for 1 1, let me map this one, then it will not be on 2 because there is no pre-image of 4, and if you try to make it on 2, then it will not be a function because every element of domain should be mapped uniquely. Is it clear to everyone? So
Yes,
finite
sir. Yes, sir.
a finite
Yes, sir.
set will never be similar to any of its proper subset. ये पॉइंट क्लियर हुआ कि नहीं आप लोगों को?
Yes sir.
Yes sir, clear है।
फाइनाइट सेट अगर आप 1 1 बनाना चाहोगे तो ऑन 2 नहीं होगा, और ऑन 2 बनाना चाहोगे तो 1 1 नहीं होगा, लेकिन उससे पहले फंक्शन भी तो होना चाहिए। फंक्शन के क्या डेफिनेशन है? यस, हाउ यू विल डिफाइन फंक्शन?
Function is a relation.
Particular type of relation which has uniquely defined. Which has a
क्या
unique
यूनिकली
image.
डिफाइंड होता है? बताएंगे जरा, इसे एलेबोरेट करेंगे, क्या यूनिकली डिफाइंड है?
A function is a relation from a set A
Hmm.
to a set B if every element of A has a unique image in B.
Yes, every element of A.
Yes, sir.
I mean every element of A should be mapped. Actually, देखो, domain codomain, unless it's a function, we should first we need to define it, and then this one domain codomain एक्चुअली बाद में कहते हैं जो लेमन टर्म है। चलो छोड़ो, खैर वो सब बातें, वो सब लेक्चर लंबा हो जाएगा, अपने काम पे आते हैं क्योंकि टोपोलॉजी पढ़ानी है। So every element of domain should be mapped and its image in B should be unique. Its image in B should be unique. I mean 2 or 3 elements can map to a single one, but this mapping is not possible, is it? Every element of domain should be mapped to unique element in set B.
Yes sir.
इसका वो नोटिस था ना, वो आपका वाला, मैंने तो वापस वही दे दिया। अच्छा, ठीक है। एंड व्हाट अबाउट इनफाइनाइट सेट? देखिए, किसी को तो पूछ लो, अभी स्टार्टिंग की क्लासेस हैं, Infinite set.
The infinite set is equivalent to its proper subset.
It will be equivalent to at least one of its proper subset. At least
Yes,
one.
sir.
हर एक के नहीं कह सकते.
At least one, yes, sir.
हाँ, at least one. ठीक है, चलो इस पे आगे बढ़ते हैं यहाँ से. अब ऐसा करता हूँ कि एक्चुअली देखो क्लास इंटरेक्टिव होगी ना तो अच्छा लगेगा, वो फिर बोरिंग हो जाता है कि, और नहीं आता आप शुरू में ही बता दो, मैं बिल्कुल बेसिक से एक्सप्लेन कर दूंगा. ठीक है, आप उसमें तो ये मैंने आप इस बुक को रीड करेंगे, उसमें सब दे रखा है डिटेल. काउंटेबल अनकाउंटेबल सेट क्या होता है, फाइनाइट सेट. यस, वेल ऑर्डर्ड सेट क्या होता है, वेल ऑर्डरिंग प्रिंसिपल क्या है. Natural number, set of natural number, or every subset of natural number has a list element. Is it? चलो इस बुक से हमें मुझे चैप्टर 2 कवर करना है. लेट अस स्टार्ट फ्रॉम दिस वन एंड देन वी विल गो टू चैप्टर 3. 2, 3 और 4. देखो आपको ये जो करना है 2, 3, 4 एंड मेट्राइजेशन थ्योरम, ऑल दीज आर इन योर नेक्स्ट सेमेस्टर. पेज नंबर 75. ठीक है, आप लोग इसे रीड करें, बोल के पढ़ने की जरूरत नहीं है, फिर उसके बाद मैं डिस्कस करता हूं. So actual whole topology is, intuition comes from line. See, whatever you have studied in the real line, Euclidean space in Rn are there already in 11th 12th class. See, we have already the concept of continuous function on the spaces on R or subset of R. Now here we are trying to generalize this concept to arbitrary set. So in real analysis, see, already we have seen definition of continuity in epsilon delta form, and with the help of distance function we have constructed balls in metric spaces, and there is equivalent interpretation of continuous function in terms of open set. Okay, we have may have studied that a function is said to be continuous if every open set in codomain has its inverse image is continuous under a function is said to be continuous if inverse image of every open set in codomain is open, or a function is said to be continuous if inverse image of every closed set is closed. So now that definition which we have studied in R, that basically all those concepts extended to arbitrary spaces. That this open closed sets, limit point, concept of limit point in real analysis we have studied, continuous functions. So now here we are generalizing all those concepts. Those corresponding ideas from real line or Euclidean space to arbitrary spaces. So here is the basic of topological spaces. History, mathematicians like Frechet, Hausdorff and others to this theory. So you can read all those concepts. Now I am starting from this topological space, definition of topological space. So topology on set X is a collection T of subset of X. Let me read it as T, and let us throughout we will use this notation T of subset of X having the following properties. A topology on a set X, X is any non-empty set. Suppose X is any non-empty set, then how we will define a topology? Just go through this definition. We have to strictly follow this definition. Then if a set is given, first make its power set. Power set is collection of all possible subset. Power set is collection of all possible subset. Then from this take a collection. from this power set, take a collection. So this is what written here, that T is a collection of subset of X. Obviously, this power set of X contains subset of X. For example, if I choose X equal to 1, 2, if I choose X equal to 1, 2, then power set of X, you have already studied all these things. Then power set will be phi set X, singleton 1, singleton 2. Yes, singleton 2. So see, singleton 1, see, if you look at singleton 1, then singleton 1 is already subset of this 1, 2. Is not it?
Yes.
Every element of this set, every element of this set is already subset of this X. Can I say? Elements of power sets are subsets of X.
Yes, sir.
So T is said to be topology. This T which we have now from this power set of X, let me take this. T is equal to say phi X singleton 1 and singleton 2 only. Singleton 2 only. I have excluded this one, this 1, 2. I have okay, sorry, this X is already there. So see, T is here. Okay, in this book there is one more notation. Actually, throughout this book, this notation is used for this one. And for proper set, for proper subset, actually this notation is used. Is it clear to everyone? See, it is important that which book you are considering. So just go through its first page. On that, it is mentioned that for A is proper subset of B. A is proper subset of B will be denoted by this notation. And this here stands for this one. So whenever I say that even if I write that T is subset of power set of X, this means T can be equal to P of X or T can be a proper subset of X. Both options are there. So this one is the notation of this book, Munkes. So for T to be a topology, for this collection to be a topology, the requirement is that empty set and the full space must be present in that set T, and union of elements of any sub collection of T is in T. Union of elements of any sub collection, I mean arbitrary union of the members of T should be again in T. And the intersection of the elements of any finite sub collection. Look here, with intersection we are restricting it to finite. So finite intersection of the members of T should be again in T. Arbitrary union, here this stands for arbitrary. What do you mean by arbitrary union?
Sir, any index set, it means nothing.
Okay, mean nothing. What do you mean by nothing? Union of elements. ठीक है, सेट थ्योरी आप लोगों ने बहुत पढ़ा है, प्लस 2 में भी पढ़ा, 11th 12th में, और उसके बाद भी रियल एनालिसिस में पढ़ा, मैट्रिक स्पेसेस पढ़ा, और सेट थ्योरी अलग से कोर्स भी है. मुझे बताया था यूनियन ऑफ एलिमेंट्स ऑफ एनी सब कलेक्शन ऑफ टीज इन टी का क्या मतलब हुआ. इस यूनियन को अगर मुझे मैथमेटिकली रिप्रेजेंट करना तो मैं कैसे लिखूंगा, क्या लिखूंगा, इस यूनियन को मैं क्या लिखूंगा, कहां से कहां तक होगा. अब ये तो चीज पीछे.
I belongs to the index set.
Okay, I belongs to the index set. And what about that index set?
Sir, either it is union union of infinitely countable, or it is finite countable.
Can I write this one? Say members of T. Let me denote members of T. Can I denote the members of T as B, T1, T2, T3? I mean, can I write this one? I is equal to 1 to say N or infinity, and
No,
Bi
sir.
is?
No, sir. No, sir.
Yes. This is not in general true. Why?
Because sir, it is for countably.
Yeah.
I can count, but
Good. Very good.
Means, sir,
This
Countable
listing,
union.
yes, this
This is
listing is only
finite.
for countable set. But here we are referring it as arbitrary. So this arbitrary union can be finite, can be countably infinite, can be uncountable. So I always write union of where I belongs to index set, where I belongs to index set. That index set can be countable, can be uncountable. Okay. So never use this notation I is equal to 1 to n, because we cannot list them in general by say members like B1, B2, yeah, T1, T2, T3. Reason is that this listing with the set of natural number, with the index of natural number, we can only do it when this set is countable, when this set is countable. Okay. So I will explain it by example. And the third requirement is that intersection of any finite subcollection of T is in T. So if that collection, this collection T, which we have taken from power set, if it satisfies these three conditions, then we say that T is a topology on X. Look at the notation. Then T is said to be topology. Then T is said to be topology. Topology on X. On X. And X together with this T is said to be topological space. Just like metric spaces. X together with the metric D is called metric spaces. But there is a huge difference between topological spaces and metric spaces. We will see that every metric space is a topological space, but topological spaces need not be a metric.
Yes, sir.
Because for metric, we need to equip it with a distance function. So in topological space, a distance function may not be there. Because here just I have taken a set equipped with some collection of its power set. Here we are not talking of the distance function. Is this clear to everyone? टोपोलॉजिकल स्पेस में अभी तक जो मैंने बात की वो एक सेट की और एक ये टी कह लो या टाउ कह लो, जो भी नोटेशन हम थ्रू आउट में हम टी यूज करेंगे, टी फॉर दिस नोटेशन, ऐसे ही चलो लिखो. सो एक्स क्या है, कोई नॉन एम्प्टी सेट, एंड व्हाट वी मीन बाय टी. टी इज बेसिकली सबसेट ऑफ पावर सेट ऑफ एक्स. सो टी इज आल्सो अ कलेक्शन ऑफ सबसेट्स ऑफ एक्स. टी इज आल्सो कलेक्शन ऑफ सबसेट ऑफ एक्स. तो अभी तक ये सेट लिया और उसके सबसेट्स का कलेक्शन, कुछ उसके सबसेट्स का कलेक्शन लिया. अभी तक मैंने थ्रू आउट कहीं भी डिस्टेंस फंक्शन यूज नहीं किया. यही बेसिक डिफरेंस है, क्योंकि टोपोलॉजी के डेफिनेशन में कहीं भी डिस्टेंस फंक्शन का कॉन्सेप्ट नहीं है. वो अलग बात है कि बाद में वो ओपन सेट मैट्रिक्स से भी, कुछ टोपोलॉजिकल स्पेसेस में जो ओपन सेट बनते हैं वो मैट्रिक्स से इंड्यूस होके आ जाते हैं. लेकिन जनरली जब जनरल टोपोलॉजी के डेफिनेशन यूज करेंगे, सो वी नेवर मेंशन ऑफ मैट्रिक. So properly speaking, a topological space is an ordered pair X equipped with this collection T consisting of a set X and a topology T on X. But we often omit specific mention of T if no confusion will arise. So in short, I will say that X is a topological space, means X equipped with a topology T. ठीक है? And once it's a topology, once it satisfies all these three conditions, then every member of the set T, every member of the set T is said to be open, is assumed to be open. देखो यहाँ पे ओपन सेट की डेफिनेशन अलग है. आप एक बार X पे पावर सेट से कलेक्शन लिया, and if that collection satisfy these three conditions, then we say that T is going to form a topology, and once it's a topology, every member of that set is said to be open. Every member of this set is said to be open. तो जो डेफिनेशन दे रखा है आपको उसके रिलेटिव थिंक करना है. प्योर मैथमेटिक्स की पहली पहचान यही है कि जो आपको डेफिनेशन दिया गया आपको उसके रिलेटिव देखना है. क्लियर हुआ यहाँ तक? मैं इसको एग्जांपल्स और समझाता हूँ आपको. देखो ओवरऑल क्या मिला, हमें कोई एक नॉन एम्प्टी सेट दिया. नॉन एम्प्टी सेट इसलिए ले रहे हैं हमें ट्रिवियल केसेस, नॉन ट्रिवियल केसेस डिस्कस करना है. ठीक है. सो जस्ट टेक अ सेट, make its power set, from that power set take a collection and claim that that collection is topology or not. That collection will still be said to be topology if phi and X full space and the empty set should be in T. Union of arbitrary sub collection of T should be in T, and the intersection of elements of any finite sub collection of T is in T. So any set X equipped with this topology is said to be topological space. X together with this T is said to be topological space. Now go through this definition, this example, and it is assumed that if X is, once X is a topological space with a equipped topology T, we say that a subset U of X is an open set if X of X is belongs to the collection T. Using this terminology, one can say that a topological space is a set X together with a collection of subsets of X called open sets, such that phi and X are both open, and such that arbitrary union and finite intersection of open sets are open. एक काम करो, इसको और क्लियर करने के लिए एग्जांपल 1 आप पढ़ो, उसके बाद मैं इसको डिस्कस करता हूं. ये तो थ्योरेटिक हो गया, कुछ एग्जांपल्स देखते हैं इसको और. देखो, a set is given consisting of three members. Now we want to make topology from on this set. So first of all, write its power set. ठीक है, तो पावर सेट आप जानते हैं सर क्या होगा. ये जस्ट समझाने के लिए, जरूरी नहीं हर जगह पावर सेट, क्योंकि अब ये तो यहाँ सेट फाइनाइट है. इफ दिस सेट इज इनफाइनाइट, देन पावर सेट विल कंटेन, I mean, it may contain uncountable members. Okay, infinite members. So we are not going to listing only. We will talk in case of countability. But since here set is finite, so let me just write it to explain you. So phi x all singletons 1, 2, 3, and then 1, 2, 2, 3, then 3, 1, 3. And then the full space X.
1, 2, 3.
Sorry, that is already there. X is already there. Okay. So this one is the power set. Now from this, you need to choose collections. That collection may be of this type. Say this one. This diagram basically, let me call it as T1. T1. So T1 is here A, singleton A. And in this we have A and B, so let me write this A and B, and then C are enclosed in this one, I mean full space X. And see, to make topology, the first condition is that phi and empty set should, phi and the full space should also be there. So X is already there, so let us put phi inside it. Now my claim is whether T1 is a topology.
Yes, sir.
This one is a topology. See, the first requirement is, if T is a topology, then phi and full space X should be there. So you can see that phi and full space X is there. First condition is true. Now second, arbitrary union of elements of sub collection should be in T. So from this, take any union.
Yes, sir.
Whatever members you are taking, its union should be again in this one. So if I take phi and X, its union will be X. If I choose phi and A, its union will be A. Already A is there in T1. If we take A and AB, then its union will be AB. Already it's there.
Yes, sir.
So everywhere it is satisfying. A and X, union of A and X is X. Already it's in T1. Now what about its finite intersection? So let me take intersection of A and AB. Intersection of A and AB is A. A is already there in A. See,
yes, sir.
Of A and AB is A, and this belongs to T. This is subset of T1. Sorry, here it is considered as a member. So just write belongs to T1. Here it is a member of T1. So write belongs to. A belongs to T1. Again, if we take intersection of AB and X, it will be AB. So already it's in T1. So this T1 is going to form a topology on this set X. This T1, this diagram is going to form a topology on this set X. And once it forms a topology, we will say that phi and X are always open.
Yes, sir.
Yes, sir.
Singleton A is open and singleton AB is, this set AB is also open. So when it's formed a topology, then every member of this set is assumed to be open. ये माना गया है, ठीक है ना। यहाँ पे देखो दिया है ना कि वंस इट्स अ टोपोलॉजी,
सर उसके एलिमेंट्स ओपन हो जाएंगे।
हाँ, एवरी मेंबर इज अज्यूम्ड टू बी ओपन। ठीक है, तो डाउट तो नहीं आता किसी को?
नो सर।
डाउट है तो आप पूछ लें। देखो सेकंड में भी
Okay, sir.
सेकंड टोपोलॉजी बिल्कुल बेसिक करा रहा हूं अभी। तो जैसे फाइनाइट कलेक्शन है, इंटरेस्टिंग तब होगा जब कुछ इनफाइनाइट हो रिप्रेजेंटेशन, लेकिन आप ये छोटी छोटी चीजें समझते चलो। अब ये जो लिखा हो इसे रीड कर लो। तो आप एक सेट पे बहुत से टोपोलॉजीज बना सकते हो। ठीक है, तो आप इसे कर लेना। ए बी को परम्यूट करके बहुत से बना सकते हो। आप लोगों की अगली क्लास है क्या? क्या
यस सर, सर लिंक भी आ गया है।
लिंक आ गया।
ठीक है, तो मैं यहीं क्लोज करता हूँ। कल रिवाइज करके आएंगे तो क्लास और इंटरेस्टिंग होगी। थोड़ा पढ़ के आएंगे आप लोग।
ओके सर।
थैंक यू सर।
सब्जेक्ट बहुत इंटरेस्टिंग है, आप थोड़ा सा रिवाइज करके आओ। अगर पहले भी नहीं पढ़ा तो कोई घबराने की जरूरत नहीं, मैं बीच में थोड़ी देर चीजें रिकॉल करा दूंगा।
बिल्कुल सर।
ओके सर।
ओके सर।
लेकिन क्लास मिस नहीं करेंगे टोपोलॉजी
थैंक यू सर।
थैंक यू सर।
थैंक यू सर।
थैंक यू सर। नमस्ते सर।